good evening, good afternoon, Borada, wherever you are, Prananda, wherever you are. Back. This is another one on the bending moment diagrams. We've just done bending moment with a 2-point loads. This one is bending moment diagram with this beam with just a UDL. It's the same one we did for this shear force, which we did previously. So make sure you watch that one first, because that's where I show you how we worked out these reactions. Which you need to get correct, because if you don't get the reactions correct, everything else is going to be wrong. So in that video, I explain how we got these two reactions by here. HEI. So we've got a draw or sketch. Don't forget, draw means use a bit of graph paper. Sketch means paper and ruler, perhaps. Right? So bending moment for the beam above, it's got one UDL across the entire length of the beam. We need to work out the bending moments at each point of this beam. So the first thing you do is work out these two reactions, which we've done here and here. Did that in the previous example. If you haven't watched that video yet, go and watch that. So this beam has got 7.5 coming up here, 7.5 coming up here. And if you remember, that plus that has got to equal what's coming down. So what's coming down is this really, 1.5 times by 10. So all of that 1.5 kilonewtons per meter combined over the 10 meters gives me 15, look, which really is 7.5. So this beam is going to bend something like that, isn't it? Because you've got a 15 coming down there, really equivalent. So it's going to bend like that. Obviously a bit more accurate than that because it's a symmetrical beam. The force is going to be in the middle, if you remember when we worked these out. So the maximum bending moment is going to be x equals 5. Because we did a shear force diagram on this one. Make sure you watch that. And don't forget, shear force diagrams will tell us where the maximum bending moment is, because where there's zero shear force, which this is the diagram we did, where there's zero shear force, which is here at x equals 5, zero shear force, maximum bending. So when I'm drawing my bending moment diagram, which is going to look a bit like that, the top of this curve is where maximum bending is, which is going to be x equals 5. Hoping. So it's always a good thing to do, like I mentioned in the previous video, draw the shear force diagram and the bending moment diagram on the same bit of paper if you can, so these points match up. But let's get on with working the numbers out. So with a UDL bending moment diagram, you need to use the UDL value. Don't use that 15. Use this value here. The 1.5 killer. Don't forget killer. So we're going to go x equals 0, 2, 4, 6, 8, 10 and work out the bending moments at each of them points. Don't forget, bending moment is force times distance. So we'll be looking at that. And don't forget, these are killers. Clockwise is positive, anti-clockwise is negative. That's meant to be a W. So clockwise is positive, anti-clockwise negative. So another little thing that you need to know about, don't worry too much where it comes from, because it comes from a bit of integration really, but we don't need to know that yet, unless you do HNC or... So to work out the bending moment due to a UDL at a certain point, we've got to use this little thing by here. Wx squared over 2 But W is just the UDL value. So in our case, the W or the UDL value is going to be 1.5. Doesn't change, 1.5 all the way through. X squared just means the distance. So for example, when I go to X equals 2, this X will be 2. Squared, it's the X squared times by W, right? All divided by 2. 2 is just 2, it'll be there forever. That's what you see here, look. So when I do these numbers, that's what I'm using. WX squared over 2. W is the UDL value, 1.5. When you're in the UDL, you've got to use this little term. Okay? So, first one I'm going to go to, x equals 0. What can I see at x equals 0? So all I'm going to look at, x equals 0, is that all I can see, I'm not in the UDL yet, because I'm not, because I'm just at x equals 0. I can see 7.5, but because I'm directly below it or above it, all I can see is 7.5 times by 0, because distance is 0. So x equals 0. 7.5 times by 0. There's the mistake I made. For some reason I thought 7.5 times by 0 is 7.5. So just make sure you check your answers. So 7.5 times by 0 is 0. Like in the previous problem, it starts off at 0. It's going to end up at 0 if everything is correct. So I've done that one. Now I'm going to go in x equals 2. So x equals 2 is about here somewhere. So all I'm looking at now is what I can see. Ignore this bit, ignore this, just what here. So I can see 7.5, I'm 2 meters away from it. And I've also got now, I'm 2 meters into this UDL thing. So I've got 2 meters worth of the UDL. So here's my term, WX squared over 2. W is 1.5. X is going to be 2 because I'm 2 meters in. So here's my bending moment. There's my 7.5 times by 2. Gone up by 2, look. That's my reaction. 2 meters in, 7.5 times by 2. And I've got now WX squared over 2. I'm 2 meters in, so 1.5 is my W value. 1.5, 1.5. Don't forget the K at the end. X is just how far I'm in, and I'm in 2 meters, so that's a 2. 2 squared on all over 2. 2 is just 2. That will give me the bending moment at that point due to that reaction and this 2 meters worth of my UDL. So when you calculate 7.5 times by 2, that's going clockwise, look. You can put a bracket around that if you want to. This one is trying to go anti-clockwise with it. So we'll do that. We'll do this and we'll do 1.5 times by 2 squared. Right, just square the 2, don't square the 1.5. Come down, put 2 in there, look, 2, come back up, put bracket in. 7.5 times by 2, take away 1.5, 2 squared over 2. Press that, it should give us 12. 12 kilonewtons per meter. So at x equals 2, I can plot 12 kilonewtons, don't forget the K. Now, that's that one done. I'll go to x equals 4 now. So x equals 4, I'm going up by 2. So all you've got to worry about now is what you see at x equals 4, which is going to be there somewhere. So ignore this, just look here. So I see 7.5, I'm 4 meters in. So I see 7.5 times by 4. And I'm now 1.5 is my UDL and I've got 4 meters worth of it. So 4 meters in, 7.5 times by 4, 2, 4, 2, 4. Here's my wx squared over 2. W is still 1.5, doesn't change. All's gone up is my 4. The 4's gone up because I'm 4 meters in, 4 meters in. I was 2 meters there, I was 2 meters there. This one is 1.5 times by 4 squared all over 2. So if you want to, once you've got this in your calculator now, you can leave it in and try and be clever. So saves doing all of that, so you can just do this. I'm going to put a 4 in there, come back a bit with this, and I'm going to put a 4 in there. Alright, make life easy for yourself. So 7.5 times by 4, take away 1.54 squared over 2. Press equals 18. 18 kilonewtons per meter. So it's going up. There's more of a bending moment there than there is at x equals 2. Don't forget, bending. The maximum bending moment is where failure may occur. Now, I've gone x equals 5 because, and I'll tell you why, because we drew the shear force diagram for this in a previous video, and it told us that the maximum zero shear force was at x equals 5. Here, look. Did this previously. So the shear force tells us at x equals 5, zero shear force, and we know that zero shear force is where the maximum bending is going to be. So that's why I'm doing x equals 5, and that's why you should draw the shear force diagram first. Because if you did x equals 2, 4, 6, you're going to miss the maximum point. So always draw the shear force diagram first, because that will tell you where your zero shear force is. So that's why I'm doing x equals 5, because I want this point here. So at x equals 5, all that's changing is this is going to 5 and this is going to 5. That's all that's changing, because that's 5. So at 5 meters in, all I can see is what I can see to the left, to the left, to the left, to the left. I can see this. So I've got 5 meters worth of this. So I can see 7.5 is the force times by the distance 5. So I've got 7.5 times by 5. And I've also got 5 meters worth of this UDL, which is still 1.5. So there's this, look, 7.5 times by 5. It's just going up, look, 2, 4, 5. So whatever we've got here, we've got here. And then I've got still 1.5, it's just got 5, because x now is 5, x now is 5, x now is 5, was 4 there, look, now it's 5, 5 squared. Hopefully this will give us the maximum bending moment, because our shear force diagram said at x equals 5, we've got 0 shear force, which means we should have maximum bending. So hopefully when we get to there, this will be a maximum. So all you've got to do now really is change a couple of numbers in here. Go back, change that to a 5, come back, come back, come back, come back, and change that to a 5. Press equals 18.75 kilonewtons per meter. So hopefully this now, when we plot it, it's going to give us something like that. That is where our 18.75 is going to be. So we'll go to x equals 6, and you should know that now, because this is fairly symmetrical, that once we've gone past the maximum bending, we're going to be coming down a bit. And because it's a symmetrical beam, the force is in the middle. When we're coming down the other end, we should be getting similar answers, look, which we do. Because it's got to come back to 0 there. So at x equals 6, all that's happening is we're going up by 6. So everything goes up now by 1, because we've gone from 5 to 6. So everything's going up to 6. 1.5 is still the W value. And we are x equals 6, we're there somewhere. So we've got 7.5 times by 6, and we've got 6 meters worth of our UDL, 1.5 kilonewtons per meter. We've got 6 meters of the thing. So keep that in your calculator because we're just going to add up to 6. So 7.5 times by 6, 6, 6, 6, 6, 6. And then that's my UDL, 1.5, 6, 6. Squared over 2. If you notice, that is 6, 18, 4, and 18. So these points here, there's 4, look, and there's 6. So it's coming down now a bit. Same thing will happen with the 8, look, the 8 and the 2. So there's the 2 and there's the 8. So, and then 10 will be 0, which is going to be there, and when x was 0, that was 0. So nice symmetrical. So, but we'll go to x equals, what are we on? 6, we'll go to 6, just put 6 in there. Go up 1, if I can, put a 6 in there. Save doing it all in one go. Can I do that? No, I don't know. No, I think it would. That'd be too clever. Not touch screen more, is it? 6 equals that. 18, look, lovely jubbly, kilonewtons per meter. So it's coming down, so that's good. This is the important point, because that's where maximum bending is. Maximum bending, that could be where failure is going to occur. Which, if you think about it, that is where this bend is going to go like that. It's going to bend like that. Really, isn't it? If you bend a ruler in the middle, it's going to bend like that. Anyway, that diagram looks a bit messy, so we'll get rid of all this. Right, so we've got the maximum bending moment, and it's all coming down now nicely, back to 0. So 18.75 at x equals 5, which does match up with this 0 shear force maximum bending thing. So I'll go to 8 just for a laugh. So what's happening now? I've gone 8, there's 8, and there's 8. 8, 8, 8, 8. So I'm 8 meters in. I'm 8 meters in. Get rid of that. Rubber, more, come on. Why isn't it working? Rubber, rubber, rubber. Why is that working? Rubber. That's interesting, Mr. Bond. Not weird. Can't draw. Press pause right there. Alright, problem solved. Problem solved, I think. Yeah. Don't know why, it's just a jig about a bit. Alright, x equals 8. So we're here somewhere. X equals 8 is there. All I'm looking at is 7.5, and I've got 8 meters worth of it. And then I've got 8 meters of this 1.5. So 8, everything's gone up to 8, 8, 8. Wx squared over 2. Nothing's changing apart from the 8. So we're looking at to get 12 because it's symmetrical. So there was 12 on the 2 coming up, and there's 12 on the 8 coming down. So in your calculator, if you've still got that in there like that, just get rid of that and put the 8 into there, and then put the 8 into that one there. Press equal, you should get 12, which you do. It's coming down nicely. So we can plot something like that. And the last one is 10. Hopefully it'll be 0. Well, it is 0. So at x equals 10, get rid of all of this now. At x equals 10, we've got all of this. So at x equals 10, we can see 7.5 times by 10 because it's 10 meters away. I've also got 10 meters worth of this UDL. I've also got the 7.5 coming up, but because I'm directly beneath it, it's going to be times by 0 because there's no distance away from it. We're only looking what we can see. And now we can see all of this now. 7.5 is there, but it's not creating a moment, so it's going to be times by 0. So 8, 8, 10, 10, 8, 8, 8, 10. What I could do is you could put that in there, couldn't you? You could put that 7.5 in there, times by 0 really, but it's going to be 0, so you could do this now. I don't know why I keep doing that. So in there you could put 10, delete 10, and then 7.5 times by 10. So that's all of that, look. And if you wanted to plus this 7.5 times, but I won't bother because it's 0. But I suppose there is a force there, but it's not making much difference. 75. Huh? Plus 7.5 times by 10 times by 0, because it's not this one, is it? That's what I've done there. Look, always check. It's 0, Morg. Always check. 0. So, 0. So that's 2, 4, 5, 6, 8, 10. So that will tell us the bending moment at each of them points, and we can plot the graph. Like I say, you'll get a question where it says draw the shear force and bending moment, so I would draw them both on the same graph. So you can make sure that this point and this point, because these points should match up, shouldn't they? Because they should do. X equals 5, X equals 5, 0 shear force, maximum bend. So all you've got to do now is plot your graph, plot your points, use a bit of graph paper if you want to. X equals 0, 0. X equals 0, 0. Don't forget this is X is meters, so put that on there. 2, 4, 5, 6, 8, 10. This is bending moment in kilonewtons per meter. So 18.75 is the maximum amount, so I've gone to 20. So at X equals 2 we got 12, X equals 2 we got 12, X equals 4 we got 18, X equals 4 we got 18, X equals 5 is the top of the curve, 18.75, 18.75. I would label it like that. Point of failure due to bending, purely bending. Maximum bending moment at 18.75 kilonewtons per meter at 5 meters from the left or 5 meters from the right. And then we're coming down, so 6 is 18, so 6 and 18 is there, look. 6, 18. 8 is 12, 8 is 12, so lined up. And then 10 is 0, so 10 is 0, lined up. So that is our bending moment diagram. Try and draw it by freehand if you want to. So, like I said before, if you hadn't done X equals 5, it just looked a bit stupid and you'd have missed this point. So you need to do this diagram first. Draw the shear force diagram first, because that will tell you this point, X equals 5, and then you can make sure that you do X equals 5 to get this maximum bending. Because 18.75 is the maximum bending moment. That's where failure and death could occur, being dramatic. Purely bending though, don't forget. So very rarely in life do you get just bending. So that's a bending moment diagram for a beam with just a UDL. So shear force diagram of beam indicates 0 shear force at X equals M. X equals M. X equals 5 meters. So, and then our bending moment diagram backs that up with a maximum bending moment of 18.75 at X equals 5. So 0 shear, maximum bending. So that is a beam with a UDL. We've done a beam with a 2-point loads. This one was a beam with just a UDL, and the next one is going to be a beam with a UDL and a point load. So that one's coming. So I will do that then. No star.